So yeah, I have quite a sort of long-standing interest in, let's say, geometric representations of knowledge. And so obviously in the last sort of 10, 15 years, there's been a lot of work on representing knowledge graphs in a geometric way, so using vector space embeddings. But in practice, of course, we don't just want to represent knowledge graphs. There are also rules and maybe ontologies and sort of more sort of generic knowledge that we also want to represent. And so I've been interested in looking at ways in which we can represent rules in particular using such representations. So let me just give like a quick example to sort of set the scene, let's say. So on the left-hand side, we have a knowledge graph, so just a set of relational facts. And so knowledge graph embedding methods, as I assume most of you will know, learn a vector space representation in which each entity from the knowledge graph is a vector. So here this is illustrated on the right. So we have the entity given de Bruyne, which corresponds to an entity here. And then we have this other entity, the Belgian national football team. And so in the knowledge graphs, they are related to each other by the member of sports team relationships. And in knowledge graph embedding models, these relationships are also represented geometrically. And so here in this example, this is the maybe one of the simplest but best known models, which is called Trans-E, where relations are represented as vector translations, right? So the triple that Kevin De Bruyne is a member of the sports team, Belgian national football team, is represented geometrically by the fact that if we add this translation vector that corresponds to the member of sports team relationship, if we add this translation to the representation of Kevin De Bruyne, we end up with the representation of this other entity, Belgian national football team. And so when we represent the knowledge graph, of course, we don't just represent a single triple, we represent in a single space essentially all the triples that we have available. And so that leads to a certain sort of spatial configurations of these entities, which ideally will represent the facts from a knowledge graph, but they will also represent additional facts, right? So here in this toy example, we may imagine that this relation country for sport is also represented by translation, and that's because the two triples that we represented before are satisfied, then automatically in this space we also see that the triple that Belgium national football team has a relation country for sport with Belgium is also satisfied, even though it wasn't in the original knowledge graph. So this is sort of, I mean, if you think about this from a sort of conceptual point of view, this is similar to rule-based reasoning, right? So we have a way of representing triples, which is such that whenever these initial two triples are satisfied, then there's a third triple that is also satisfied, right? So there's a certain type of regularity which is captured by these geometric representations that feels very much like a rule. Okay, so just to summarize this, so we want to learn geometric representations of knowledge graphs, and depending on the kind of model that we use to do that, how exactly we represent relations, we are encoding certain types of regularities or inductive biases, and somehow, this connects to rule-based knowledge. So we want to make this explicit, and this is useful or potentially useful, because if you have a single geometric representation that can capture the facts from a knowledge graph, but also somehow can represent rules, this could be useful. If you have an ontology available, for example, we can use this to regularize the embedding, so as an additional supervision signal to make sure that we're not capturing nonsensical things. We can use this for inductive knowledge graph completion. So this is where you have new entities that emerge after your embedding model has been trained. So we want to make sure that we can deal with these new entities by just learning additional entity embeddings without having to relearn the rest of the knowledge graph embedding model. Intuitively, that can only sort of work if the knowledge graph embedding model is sort of rule-like, and so this is something that we want to explore as well. And then explainability, for example, is another advantage. If we can really connect knowledge graph embedding models to rules, then that gives us a way to explain what the model has actually learned, but by just making explicit what are the rules that are captured by the model. So that's just sort of basic motivation. Now, the problem is that, even though intuitively what these knowledge graph embedding models do has some relationship with rule-based reasoning, we have to make this explicit, right? And this is where these region-based representations come into play. So the first part of the slide, I'll talk a little bit more about these region-based embeddings in general, and then I'll move on to some specific implementations that we've been working on in the last year or so. Okay, so region-based embeddings. So the idea is the idea is basically that the intuition comes, or the inspiration comes from this theory of conceptual spaces. So the idea is that entities are vectors or points in some space, and predicates are represented as regions. And typically, these regions will be convex. So if we have a unary predicates, so concepts, we can represent them as regions in the embedding space. So here, for this example, we have, just for simplicity, a one-dimensional space. In practice, of course, they will be much higher dimensional, but just for this example, let's consider a one-dimensional space. So points in the space correspond to entities. So in this toy example, these entities may correspond to specific animals. So we have this point here that corresponds to lion. And then we have regions that correspond to concepts, right? So we have a region for the carnivore concept. And so we can see that lion, the point that represents lion, is inside the carnivore concept. And so that represents the knowledge that every lion is a carnivore. And so the basic point is that the spatial configuration of these regions also captures knowledge, right? So here we can see that herbivore, omnivore, and carnivore are sort of disjoint regions. And so that represents the knowledge that they are disjoint concepts, that no entity can be more than one of these. We can also see, for example, that the carnivore region is included in the animal region. So this red animal region. So that represents the knowledge that every carnivore is an animal, right? So the basic idea is that, rules, if you want, or sort of generic knowledge is captured by the spatial configuration of these concepts. Now, we can do the same with binary predicates, so with relations, by basically taking the Cartesian product of the entity embedding space with itself, right? So now, every entity corresponds to has a representation here on the x-axis, and every entity also has the same representation here on the y-axis, right? So if you look at this two-dimensional space, then each point in the two-dimensional space represents a pair of entities, right? Where the first entity is the entity that corresponds to the projection on the x-axis, and the second entity is the one that corresponds to the projection on the y-axis, right? So here, this point represents the pair lion-zebra. Again, predicates, in this case, now binary relations, correspond to regions. So here we have this orange region, which is the eats relation. So the point lion-zebra is inside that region. So that captures the knowledge that lion eats zebra, right? So this is very similar to what, conceptually similar to what the knowledge graph embedding model would do. It captures geometrically the fact that the triple lion eats zebra is satisfied. But as before, we can do more than represent these facts. We can also represent rules based on how the spatial arrangement of these regions is. So here in this example, for example, we have the rule: if X is a carnivore and X eats Y, then Y is an animal. So that rule is satisfied in this representation. So why is that the case? Well, it means that whenever we have a point, like this lion-zebra point, which is such that the point itself is in the eats region, so in other words, eats XY holds, and the first entity, so the projection on the x-axis, is in the carnivore region, right? So this is the first argument. Then it will always be the case that the second entity, so the projection of the point on the y-axis, is in the animal region, right? So it's slightly more complex to sort of imagine than in the one-dimensional case, but it's essentially the same thing, right? So the spatial configuration of these regions determines which rules are satisfied and which are not. So we can do the same even with existentials. So in this example, we also have that if X is a carnivore, then always there exists a Y such that X eats Y and Y is an animal. So again, why is this the case? Well, whenever we pick a point on the x-axis which belongs to the carnivore region, then it is always possible to find the corresponding y coordinates such that this point in the two-dimensional space is in the each region, and such that the projection on the y-axis is in the animal region. Right? So that's sort of the spatial counterpart to this existential rule. So this is sort of the general framework that we have in mind when we talk about region-based models. Now, in fact, this is nothing very special, because existing knowledge graph embedding models we can essentially also think of as region-based representations. It just requires us to put a threshold on the scoring function, right? So this trans-E model that I mentioned before, what it does is to each triple, it assigns a score depending on the spatial configuration in the embedding space. But if we put a threshold on that score and say, look, every triple that has a score that's above this particular threshold, we assume as being captured by the embedding. So as soon as we put that threshold, we end up with a region in space that corresponds to those triples that are satisfied. Right? So here in this example, so it's the same as before. We have the two-dimensional space here is really the Cartesian product of the embedding space of the trans-E model with itself. For simplicity, again, I'm assuming here the embedding space is one-dimensional, so the Cartesian space is two-dimensional. So each point in this two-dimensional space is representing a pair of entities, and any pair of entities whose representation is in this in this green band will be treated as having the relation that's being modeled here, let's call it R, as having the relation R by the trans-E model, right? So all the triples all the pairs of entities that are assumed to satisfy relation R, that are instances of relation R, in this two-dimensional space are located in this sort of unbounded convex region, and so we can do the same with basically any knowledge graph embedding model. We just put a threshold on the scoring function. The only thing that differs is the shape of the regions, right? So for example, if you use disk nulls, we have this hyperbolic region that contains the entity pair representations that are assumed to have the relationship. Right? So I hope that's sort of clear. Okay, so now so what this basically does is it links knowledge graph embedding models to regions, and as I sort of sketched before, once we have regions, we can look at the spatial arrangement of these regions, and we can use the spatial arrangement to decide if a rule is captured or not captured. So let's make this a bit more precise now. So yeah, we have a geometric representation in which every entity A is represented by a vector, so we can call it eta A, eta of A. So the geometric representation of A, which is a vector in n-dimensional space, and then a k-ary relation R is simply a region. So often we'll assume this to be convex, but that's sort of not essential. It's a region in a space that is essentially the Cartesian product of the embedding space k times with itself, right? So if entities are represented in n dimensions, then this region will be having k times n dimensions. And once you have this basic view, then if you want to check if some relational facts are applied to the arguments a1 to ak is captured by the embedding space, all we have to do is we take the representations of the arguments a1 to an, we concatenate them, so that this plus symbol here is concatenation. So we concatenate the embeddings of the arguments, so that gives us a vector in k times n dimensions, and then we simply check if that vector belongs to the region that represents the relation R. Right? So that's the basic idea. Okay, so now that we have this this view of relations as regions, so we can check relational facts, but we can also check rules. So just to illustrate this, if we have a very basic rule, so if S applied to some tuple and T applies to the same tuple of arguments, then it always holds that R belongs to that tuple of arguments, right? So if you have this kind of rule, then straightforwardly we can interpret it geometrically in terms of intersections and inclusions, right? So this rule here, it really means if we think about it spatially, that the regions representing S and T, their intersection is included in the region that represents the relationship R. So if we can show this in a picture even. So here we have binary relations. So if each entity is represented in a one-dimensional space, the relations are represented in two-dimensional space. And so here we have a model of this rule, right? Because we have regions which are such that the intersection of the representation of S, so this blue region, and T, the green region, so that intersection here is included in the red region, which is the representation of R. So this rule is satisfied. Now, of course, this is a very simple rule because it's just an intersection rule where the arguments of all the predicates is the same. In practice, we're usually more interested in composition rules, like here where we have S of x1, x2, and T of x2, x3 implies R of x1, x3, right? So here, intuitively, it may be less clear how we can model this geometrically, but in fact, we can do the same thing because we can think of these predicates R, S, and T as being ternary relations over the same tuple of arguments, but each time one of the arguments is ignored, right? So for example, T of x2, xr, x2, x3, we can think of it as T star of x1, x2, x3, where the first argument is ignored. So it means that even composition rules, we can sort of think of them in terms of intersections and inclusions, but instead of a two-dimensional space, it would be a three-dimensional space. Just to illustrate this, so here we have the representation of relationship R, which is two-dimensional, right? But we can think of this as a three-dimensional region by simply extending. I mean, the third dimension doesn't matter, so we just extend it infinitely along the z-axis. So we have this sort of, so it's called a cylindrical extension of this two-dimensional region. And we can do the same for the representation of R and S. And then again, we can see that this rule, where is it? So this rule here is satisfied because in this three-dimensional space, the intersection of S and T is included in the representation of R. Okay, I hope that wasn't sort of too confusing. The details don't really matter. The main idea is that we represent relations as regions, entities as points, and the spatial arrangements of these regions determine which rules are satisfied. Now, the main question I want to talk about in this presentation today is what are the kinds of rule bases that we can capture in this way? So is it possible, for example, given an arbitrary set of rules, to find a geometric representation that exactly satisfies this set of rules? And so the answer is no. But we can give a more fine-grained answer depending on the kinds of regions that are used. So as a first sort of negative result, if we have a bilinear model, so that means a knowledge graph embedding model where the scoring function has as this particular form. So we have a matrix that represents the relationship. Entities are vectors. And then the scoring function is computed like this. And then we put a threshold on that score. So that's, that covers a lot of existing models like, like this mode and complex and this Rascal and Tucker. And so there's quite a lot of different flavors of this bilinear model, but for all of them, they have basically this particular form. They just differ in how this matrix M is constrained, right? So if we allow M only to be a diagonal matrix, then we have the dist mode model, for example. Okay, so for any bilinear model, suppose, so we take a threshold on the scoring function that gives us regions, and we want to satisfy rules according to these regions. So suppose we have rules like this. So they just say that we have relations R1 to Rk, all of which are basically special cases of the relations S, right? So if R1, then S, if R2, then S, and so on. So we want to satisfy all of these rules. Now, it turns out that any representation using convex regions is such that we can partition the set of relations R1 to Rk in two groups where these relationships hold. So it's easiest to see here on the diagram. So whenever these rules are satisfied, we will have that, we have basically two chains of relations that sort of specialize each other. So rather than having a tree where, so maybe I can draw this. So in general, what we want is something like this, right? Where we have k relations, all of which are specializations of S, but they are not specializations of each other, and that's not possible, right? We always have either one chain of relations or two chains of relations, like we have here. So that limits. It doesn't limit the rules that can be represented. Rather, it means that if we want to satisfy these kind of rules, we're always going to satisfy additional rules that we didn't intend to satisfy, which is sort of equally bad. Here's another counterexample. Not a counterexample, a negative result. So this is about disjointness, right? So if we want to capture the fact that R1 and R2 are disjoint, so that means that they are represented as two disjoint spatial regions, then well, that's not compatible with representing these facts. So if you want to satisfy these four relational facts, then it's not possible to represent R1 and R2 as disjoint convex regions. So there are limitations to what we can represent using convex regions. And the reason why we require convexity typically is because we want these regions to be easy to learn. Otherwise, there's no point in having a model that can theoretically represent everything if it's too complex to learn in practice. And so I'll talk a lot more about how we can sort of parameterize these things so that we can easily learn the regions. But in most cases, we will have convex regions. Now, we also have positive results. And so the main one here is as follows. So we're going to represent relations as convex regions, so convex polytopes. And then we can always satisfy an arbitrary set of existential rules as long as, well, that set of rules has a finite model. And the form of these rules satisfies a condition that we call quasi-chains. So basically what it means is that for every atom in this conjunction in the body, shares at most one variable with the atoms that come before it. So in the special case where the relations are binary, then that would cover basically a standard composition rules. So the importance, I suppose, is this. The result is a bit more general, but the importance is that we can capture arbitrary set of composition rules, and we've got also model extensions and so on, but that's the main idea, which I think is sufficient for most if you think about the kind of rules that are used for knowledge graph completion, then they will usually have this kind of form. Okay, so that's sort of the work that we've done a few years ago. So we have this sort of relatively nice result where we can capture at least arbitrary set of composition rules using convex regions, and so that's nice. But it's just a theoretical model because we're talking about regions that would have regions in an embedding space that has twice the number of dimensions of the entities. In a typical knowledge graph embedding model, maybe entities may be represented using 100 dimensions or sometimes even 1000 dimensions. So that means that we're talking about regions that are 200 dimensional or 2000 dimensional. We can't really learn arbitrary polytopes in these high dimensional spaces. It would be first of all too computationally complex to compute compositions and intersections of these regions, but also the model would just overfit because there would be too many parameters to learn. So we have to in practice make quite dramatic simplifications, right? We still want to represent relations as regions, but we want these regions to be simple enough that we can easily manipulate them, and that we don't have overfitting if we want to learn these models in practice. Okay, and so we came up with a solution that's based on octagons, and so you'll see in a minute why octagons. And the basic simplification that we do is so rather than thinking of learning a 2n-dimensional region, we're going to learn n two-dimensional regions, right? So the point is that so we have two entities, E and F. We're not going to compare all these two n coordinates with each other. We're just going to first of all compare the first coordinate of E with the first coordinate of F. And so we'll have a two-dimensional region that will constrain the joint values that these two coordinates can have, if E and F are instances of some relation R. And so we'll have another region for the second coordinate, and so on. So we'll have n of these regions, n of these two-dimensional regions. And then, if you want to see this in the framework of region-based embeddings, the region that represents the relationship R itself is then simply the Cartesian products of these n two-dimensional regions. Okay, so that's, dramatically simplifies the whole framework. Now, the main question that remains is, what are these two-dimensional regions? Right. So the simplest thing that we can do is go back to the trans-E model. In the trans-E model, we have these, these infinite stripes. So that's a two-dimensional region. So we'll have n of these stripes. And then that's a region, and so we the trans-E model with the thresholds is threshold on each coordinate in this case is a special case of this region-based framework, this coordinate-wise region-based framework. Okay, so is this a good model? Is this can we stop here? Well, the answer is no. First of all, the good thing about this, it's simple, it's easy to learn. And these regions are closed under intersection and composition, right? So if we have this kind of trans-E representation of two relations, we can easily compute the representation of the composition of these two relations and intersections of such representation. So that's useful. That's exactly the kind of thing that we want. So we can easily manipulate these regions. But trans-E has a lot of limitations. It's not capable of capturing arbitrary knowledge graphs. So that's a well-known result. And if we think about capturing rules, it's quite easy to see also that, it's very limited in what kind of rules it can satisfy. In particular, or as an example, it cannot distinguish between it cannot capture the ordering in which the atoms or the relationship in the body appear. So a rule like this, where we say Sxy and Tyz imply Rxz, they should say. Then here as well. Then trans-E will not be able to distinguish this rule from the rule here on the right, where we say T of xy and S of yz imply R of xz. Right? And these two rules are of course not the same, and often it's quite important to sort of separate these two. To distinguish these two rules. But with trans-E you cannot do it. Right? So that's a very unfortunate limitation. And then there are well-known constraints when it comes to modeling reflexive, symmetric, and transitive relations. There are sort of all these sort of dependencies that you don't really want, right? So trans-E can capture any symmetric relation that is captured by trans-E will always be reflexive, which we don't want, right? And yeah. So what else can we do? So there has been a recent model that is also formulated in this framework of coordinate-wise region-based models, where the two-dimensional regions are parallelograms. That's nice, because with these parallelograms, we can capture arbitrary knowledge graphs. Now we can distinguish between sort of the order in which relations in the body of a rule appear. And we are far less constrained when it comes to capturing reflexive, symmetric, and transitive relations. So this is a much more general model. We can capture a much broader set of rules, so that's good. The main limitation is that these parallelograms are not closed under intersection and composition, right? So if you have two relations that both have their own parallelogram representation, we take the intersection, we no longer have a parallelogram. If you have two regions which are represented as a parallelogram, or n parallelograms, really, then the composition of these two relations may no longer be a parallelogram. So that makes it quite, for some of the applications where we want to use region-based representations, that's a big limitation, because we can't easily enforce that the rule is satisfied or check which rules are satisfied without doing quite extensive computations, because we end up with sort of polygons that may have arbitrary many vertices. Okay, so what else can we do? So the approach that we took was to start from trans E, these sort of trans E stripes that always occur at 45-degree angles. But first of all, add domain and range constraints, right? So domain constraints. So the trans E constraint is this constraint, right? That the region is bounded by this line here and this line here, which are parameterized by these values u plus and u minus. So we're going to add 4 more constraints. So the domain constraint is this sort of the x value, right? So the embedding of the first entity, the head entity in the triple, is bounded between x minus and x plus. And then the range constraint, if you want, is that so the y value is bounded by y minus and y plus. So that gives us a region which is a hexagon, not an arbitrary hexagon. It sort of acts as a line, right? So it has two sides which are parallel with the x-axis, 2 which are parallel with the y-axis, and then 2 which are sort of at 45-degree angle. But it looks more interesting. In practice, it still has sort of some of the same limitations as trans E, so it's still not possible to capture arbitrary knowledge graphs with these hexagons. But then what we find is that we can basically add one more set of constraints to go from a hexagon to an octagon that resolves these limitations. So what we do with the octagons is, so we still have the trans E constraint, this U constraints here. We still have the X constraints and the Y constraints. But now we add one more set of constraints, which is the region is bounded by these 2 lines, which are also at a 45-degree angle, but sort of orthogonal to the 45-degree angle of the trans E constraints. So they are parameterized by these values v minus and v plus. And so that gives us an octagon. Again, it's not an arbitrary octagon. It has sort of sides which are either aligned with the axis or at 45-degree angles. But it turns out that they behave quite nicely. So these octagons, because the angles are fixed, are closed under intersection and composition. So they're very easy to manipulate, and then I'll say a bit more about that. It's possible with the octagons to capture arbitrary knowledge graphs, and we can probably capture some rules, and I'll say more about this in a minute. First, the parameterization. So we have 8 parameters. They are not all independent, right? So there's some relationships between them, which means that if we have these 8 parameters, sometimes we can tighten these parameters. We can sort of get tighter bands. The way we can sort of tighten the bands is shown here on the slide. The details don't matter at all. The point is that we can easily compute these things, right? It's just a maximum of some easily computable things. And if we do one update of the bounds, so if we apply this update here once, then we always end up with parameters that can no longer be further tightened, right? What it means in practice is that if we learn these 8 parameters for a given octagon, we can easily sort of make them tight, even sort of as part of a loss function, and so without too much hassle. We can easily compute intersections and even compositions. So I have the characterization here. Again, details don't matter at all. The point is that if we have 2 octagons represented by you have this one set of parameters for one octagon, other set of parameters for the other octagon. They both represent some relation, and the composition of these 2 relations is also an octagon. And the parameters of that octagon, we can very easily compute it. The solution is shown here, but the point is that this is analytical. We can put it in a loss function. It's sort of very easy to work with. Okay, so the main question now is, what about rules? We know that with arbitrary convex polytopes in 2 n dimensions, we can capture arbitrary composition rules. So we may wonder, is that still true if we have this octagon-based model where we have sort of pairwise approach? Now the answer is no, unfortunately. But at least we can capture a subset of composition rules, which we call regular. So what it means for a composition rule to be regular here in this context is that all the relations that appear are 1 to rk in the body and then rk plus 1 in the head. They're all different. So we can't have a rule where the same relation appears more than once. Okay, as long as that's true for all the rules in our rule base, and all the rules that are entailed by the rule base, then we can find octagons that exactly capture the rules that are entailed, that are included or entailed by the rule base, and nothing else. So no other composition rules that we didn't want to capture. So the restriction that we only have this for regular rules. I mean, it's a real restriction, right? We would rather not have this restriction, but it's the first result of this kind that that is known, that has been established as far as I know, for a model that can be learned in practice, right? So it's there are no existing knowledge graph embedding models for which this kind of result was already known to be true. So that's something that we were quite happy with. And then sort of, yeah, so we have a region-based model that is sort of simple, sort of easy to work with, and that is sort of expressive in terms of the rules it can capture. So now the question is, does it work in practice? Can we learn these octagons, and how does it compare with existing knowledge graph embedding models? So yeah, the main idea is the following. So an octagon has these sort of 4 sets of constraints, right? So you have the X constraints, which is the domain constraints, the Y constraints is the range constraint, the U constraint is this sort of trans-E-like constraint, and then the sort of dual, sort of the other 45-degree angle constraint. So that's what we have to capture. Now, these are hard constraints, but when we learn the model, of course, we have to make everything sort of differentiable, and we need to have a soft approximation of these octagons. So we take this approach. This is basically so this is a sigmoid that is. I mean, the details don't really matter. It's basically a logistic. Yeah, it's like a logistic regression loss where the hyperplane that we want to model corresponds to the side of the octagon, right? So this for a given coordinate, this will be close to 0 if a point is outside the octagon. It will be close to 1, or no, it will be positive, not necessarily 1, but it will be positive inside the octagon, and then it will sort of, it will be close to 1 inside the octagon, and it will be sort of close to 0.5 around the border of the octagon, right? So it's really just like a soft approximation of the octagon. I mean, this is the constraint for this is the sort of soft version of the U constraint. We can do the same for the other 4. And then we aggregate all these distances, I mean, the distance vector, so the sort of penalties that say how much is the constraint that a certain pair of entities should be in the octagon or outside the octagon. How much is it violated, right? And that becomes our scoring function. And then we train the knowledge graph embedding model pretty much in the standard way. So we have a typical knowledge graph embedding loss, which is this margin loss with self-adversarial negative sampling. Details don't really matter. And yeah, so we can see how well it works. So here is the results on FB15K and WN18RR, sort of the 2 standard benchmarks for knowledge graph completion. So the main competitor, if you want, is this parallelogram model, which is sort of, yeah, it's not as nice to deal with, right? Because it's not close under intersection and composition. So the octagons are sort of, yeah, easier to work with. But if as you can see here, when it comes to empirical performance, the parallelograms perform slightly better, right? So the octagons, there's a, with the octagons it's much easier to inject rules or to sort of, yeah, work with these representations. But there is a small penalty, it seems, to be paid for that flexibility. So we sort of, well, it's slightly underperform, but consistently underperform the parallelograms. That's sort of the main finding. And then, so we have 4 constraints, right? The U, the V, the X, and the Y constraints. In fact, if we drop the domain and range constraints, so we only have the U and the V constraints, the performance is really very similar. And then if we don't have the V constraints, then often, the results are still reasonable, except for hit set 1 for WN18RR. And that's because without that V constraint, we have the same limitations as trans-E. And in particular, we have this limitation that if relations are symmetric, then they are automatically also reflexive. and that leads to problems for hit set one, where the entity itself, so the head entity is predicted as the top prediction for the tail of a given relationship. So you can see that the performance is really bad, and that's the same for trans E. So that's sort of the main sort of findings. So the main thing for us was really to see that these octagons, they are really simple enough that they can be learned in practice, right? So we get a performance that is roughly on par with existing models, slightly better than some models in some cases. So for example, quite a lot better on WordNet. So WN18RR, quite a lot better than Trans E, for example. But yeah, not as good as the parallelograms. So that's something that we're still working on, sort of trying to better understand what is exactly the penalty that we pay. Why is this penalty there, right? So why are octagons performing slightly worse than parallelograms? We have some ideas. But yeah, the main conclusion is that finally we have some kind of region-based model that can provably capture a large class of rules, and that we can actually learn in practice, and that sort of performs roughly as we would want, so roughly on par with other knowledge graph embedding models. Okay, so that brings me to the last part of the presentation, where we're trying to find out now whether we can escape this limitation of the kind of rules that we can capture with octagons, right? So remember, we can capture regular composition rules. So we really want to capture arbitrary composition rules, right? We don't want this restriction to regular rules. And so my feeling, at least, is that this is very much tied to the idea that we have this coordinate-wise approach. So I'm not optimistic about chances of finding a model that can capture arbitrary composition rules that is sort of coordinate-wise, so that is using these two-dimensional regions only, without going to very exotic regions that wouldn't be practical to work with anyway. So the only other thing that we can do is have a more general approach where we have regions that compare different coordinates, right? So where maybe the first coordinate of entity one is compared with sort of other coordinates than the first coordinates of the other entity. Yeah, so I call this going beyond coordinate-wise models. Now the problem is, if we allow arbitrary interaction between all the coordinates, then again we have the same problem as in the more general case. We have too many parameters, right? So overfitting is really a problem if each relation is so in most existing knowledge graph embedding models, the number of parameters that you use for representing a relation is either the same or maybe 2 times the number of parameters that you have for representing each entity. If you go beyond that, then very quickly you get overfitting. So the challenge here is, how can we design a model that compares across different coordinates without having overfitting? So yeah, what we try to do is look at the simplest possible approach of doing this using what we call ordering constraints. So I'll clarify what this means. So this is still the same as before, right? So we have entities E and F, and E and F have belong to relation R if the concatenation of their embedding belongs to this convex region, right? So now the question is, how is this convex region defined? So with these ordering constraints, we define it like this: this vector belongs to the region if these inequalities are satisfied. Now, what are these inequalities? Well, we have to model a relation. We specify a subset of the coordinates. So this IR is, so let's say we have n coordinates, is a subset of these n coordinates. And then for each coordinate I in this set, we have this inequality. So this inequality just say that some coordinate of entity E has to be less than some other coordinate of entity F, right? And so there's not the same coordinates. So we have this mapping sigma here that decides which coordinate of E should be below which coordinate of F. Right? So it's really a very, very simple model, right? It's just a bunch of inequalities. But still, it's I mean, it's quite surprising to me, but still, this is enough to capture a lot of rules. Now, to illustrate how we can capture rules with such a simple model, I have an example here. So we have 3 relations here in this example: R, S, and T. And so, okay, this for all we can ignore. This is a mistake. The entity pair EF belongs to relation R if the second coordinate of E is below the first coordinate of F, and the third coordinate of E is below the second coordinate of F. Right? That's how the region that represents relation R is defined. And then for S, we have another inequality. So the first coordinate of E has to be below the third coordinate of F. And then T, yes, again, similar, the second coordinate of E has to be below the third coordinate of F. So that's how the regions are defined. So now, suppose we have these two triples, ARB and BSC. So the corresponding constraints you can see here, right? So because ARB is satisfied, we know that the second coordinate of A has to be below the first coordinate of B, and the third coordinate of A has to be below the second coordinate of B, and then similar for the other triple, right? So that's because of how these regions were defined. And of course, we have this transitivity here, right? A2 is before B1, and B1 is before C3. So that implies that A2 is before C3. But that was the constraints that we used to define the region that represents the relation T. So what it means is that with this model, whenever the triples ARB and BSC are satisfied, we automatically also find that the triple ATC is satisfied. So that means that in this embedding model, the rule that R of XY and S of YZ imply T of XZ, that rule is satisfied. So hopefully that gives you at least a little bit of an intuition of how we can capture composition rules using ordering constraints. Okay. An interesting sort of almost incidental finding is that we can simulate these kind of rules using graph neural networks. So the main idea is this, right? So this is the constraint that we had before, right? That's sort of the general formulation of the ordering constraints that define in some relationship R. Now this constraint we can reformulate like this. So we have a matrix. So we represent the relationship R as a matrix, which is heavily constrained. Basically, it has two constraints. All the entries of the matrix are either 0 or 1. And for each row in this matrix, at most one of the entries is 1. So most are 0. They could all be 0, or all but 1 could be 0. And so if you have such a matrix A, then we can reformulate this sort of order constraints by saying that this equality has to be satisfied, right? They're exactly equivalent. Now, why does this matter? Well, because it sort of suggests how we can learn these embeddings using a graph neural network formulation. I won't give the details because they're not too important, but basically we have a graph neural network using max pooling, and that is basically taking the same form of what we have here for the ordering constraints. And using that graph neural network, we can learn embeddings that satisfy a given set of rules, right? So the rules are really captured implicitly by the parameters of these matrices A. Once we have these matrices, then we can learn the entity embeddings by just applying the graph neural network to randomly initialized entity embeddings. Right? So that's sort of a surprising empirical finding, that we can just randomly initialize the entity embeddings, then use this GNN for a couple of iterations, and we end up with embeddings that satisfy the rules that we are given. Actually, an important point that maybe I should emphasize is that in practice, of course, we don't have the rules. Right? When we talk about expressivity, what we show is that we can capture a given set of rules. In practice, we don't have the given set of rules. We just have the knowledge graph. The reason why we are interested in modeling the rules is because we want to be sure that the embedding model is expressive enough that it is capable of capturing sets of rules. In practice, we want the embedding model to be learned from the knowledge graph alone, which should correspond to sort of learning the rules that matter for the given knowledge graph just from the data. So that's an important distinction that sometimes causes confusion, for reviewers, for example. So we're interested in showing whether or not we can capture always a set of rules of a particular format. But the reason we're interested in doing this is not necessarily because we have the rules and we want to inject them. It's just to show that, or to check whether the embedding model is expressive enough to do this. Okay, so is the embedding model, with these very simple ordering constraints, is this capable of modeling arbitrary sets of composition rules? Unfortunately, the answer again is no, but it's more interesting than this. So the first positive result is this. So if we have a set of composition rules which have the property that, they're all of this form, so with two atoms in the body. So having two atoms in the body is not a limitation, because if you have more than two atoms, we can always sort of rewrite by introducing fresh variables. But the constraint that we do have is that the second relation in the body cannot occur in the head of any rule, right? So we can have sort of recursive rules, but we can only have the recursion for the first relation that appears in each rule. So that's very similar to the definition of a left regular formal grammar. So that's why we call this left regular rule basis. So we have a negative result that also depends on sort of formal grammars that say that arbitrary rules cannot be modeled, because if we were able to model arbitrary composition rules, it would also imply that we can find a finite state machine for every context-free grammar. Now, we know that that's not true, so it follows that we cannot. So we can prove that we cannot model arbitrary composition rules. But if you restrict these to left regular ones, then it is possible. So if you have a left regular rule base, then we can find the GNN such that if you use the GNN to convergence, we end up with entity embeddings that are such that every triple that can be inferred from the rules will be satisfied in the embedding model. And every triple that is satisfied can be inferred with high probability, arbitrary high probability. Now, why with arbitrary high probability? That's because we start with randomly initialized entity embeddings. Now, if you have randomly initialized embeddings, then there's always a chance that you initialize them such that the relationship is satisfied that shouldn't be satisfied. We can make that probability arbitrarily small by having a sufficient number of dimensions, and so all the coordinates are sort of sampled independently. That's another sort of assumption I should have mentioned. And so if you have enough dimensions, then the chances of relationships holding by chance becomes sort of vanishingly small. So it's a long explanation just to say that we can basically capture left regular rule, arbitrary sets of left regular rule bases, but perfectly using just ordering constraints. So what about general composition rules? So the main result here is that we can actually capture arbitrary composition rules as long as we limit the sort of the number of inference steps that we care about. And that's usually true in practice, right? If we have a GNN, we will fix the number of layers, right? We will only apply that GNN update for a finite number of times. If you have a knowledge graph that we reason about, it will have a finite size, and so on. So we really, in practice, maybe we mostly care about bounded inference. And there, we have a much more positive result. So for an arbitrary set of composition rules, and the embeddings that we get after m iterations of the GNN for some particular m, then it's true that every triple that can be inferred from the rules in the knowledge graph with up to m steps, it will be guaranteed to be captured by the embedding. Conversely, everything that is captured by the embedding will almost certainly be inferable from the from the rules and the knowledge graph. Okay, and then I guess I should try to wrap up. So we have some experimental results. Again, I mean, this is not just like with the octagons. This is not about beating the state of the art. This is about finding a practical embedding model that we can learn reasonably efficiently, that performs on par with sort of existing models, but that has these advantages in terms of how we can explicitly model rules and the guarantees on expressivity. So here we compare our results with I mean, we can view our model as a sort of differentiable rule learning strategy. And so as you can see here, the sort of, if you compare this with other, older differentiable rule-based methods, then our approach is quite a bit better. If you compare with state-of-the-art rule-based methods like AnyBull, in most cases we outperform AnyBull, but not for WordNet. So there's an exception there that we don't yet understand very well. So that's also good. We are not competitive with state-of-the-art graph neural networks, right? So that's also clear. But by the way, these results are for the inductive setting. So this is the setting where we have two disjoint knowledge graphs, so with disjoint sets of entities, but the same types of relationships. We train the model on one knowledge graph, and then we evaluate on the second, the sort of disjoint knowledge graph. So it's a much harder problem than transductive knowledge graph completion. And intuitively, it's about capturing rules. All right, so that sort of brings me to the end of the presentation. So basically, yeah, the topic I was talking about is about region-based embeddings. The reason why we care about region-based embeddings is because we want to be able to formally capture both rule bases and knowledge graphs, and that's a lot of this is sort of still sort of open questions and future work. But the idea is that once we have a good mechanism for representing rules and knowledge in a framework that is sort of easy to manipulate and easy to learn, then we have this sort of nice interface between symbolic knowledge and vector-based embeddings, and we can do potentially a lot more than what is possible with existing models. So the sort of broader goal is to really find models that integrate learning and reasoning, which I guess is what many people are working on these days. But especially to have this much tighter integration of learning and reasoning, right? So a lot of approaches to learning and reasoning these days sort of separates the learning and reasoning parts, right? So you have a learning part that learns some sort of representations, and then we have reasoning on top of these representations, and that's a bit limited, and we sort of want to integrate this a bit more clearly, but at the same time we still want to make sure that sort of we can extract rules and we keep the correspondence between rules and embeddings. So that's how sort of we end up with region-based representations. As I mentioned, the types of regions that you use have a dramatic impact on the expressivity of the model, right? So if you have arbitrary complex polytopes, that we can capture arbitrary composition rules. With order embeddings, we can do sort of bounded reasoning with arbitrary set of composition rules. With octagons, we have a more limited result, so where we can capture only regular composition rules. Still lots of open questions, but hopefully, I've convinced you that these region-based approaches have some appeal, right? They're very fun to work on. There's some very intriguing questions that remain unanswered, and so hopefully you find it interesting. So I'm happy now to answer some questions if you have any.